we have been one of the most affected. And I think we don't need to look at a fancy model. We just look at what happened in the last 12 years in Pakistan. There was a flood in 2010 that wiped out significant areas of rice. Then we had another flood in 2022 that wiped most of the rice areas in Sindh and Balochistan. And I come from a rice production area. My parents are rice growers in Balochistan. And when I asked them when was the last flood before 2010, they tell me that it was before I was born, sometime in the 70s. So the intensity of these extreme events and their frequency is increasing. Pakistan is already considered a water-stressed country, and all climate models project that we will be one of the extremely water-stressed countries by 2040. So I think business as usual is not an option for us. If we want to keep eating rice, producing rice, and exporting it, we need to do things differently. And so we know what the problem is, and we, I think, also have some solutions. But why are farmers still using what we call sustainable practices, for example, flooding, continuous flooding system in rice? And often we blame farmers for not doing the right thing. But I think sometimes it's probably, in reality, it's other way around. DSR, for example, is a case and example. It's a fantastic technique. We considered as a research community. We published tons of papers. We thought it was the silver bullet. And we gave it to farmers, and a few years later they came back saying, well, there is a lot of issues with wheat. We can't grow this. Farmers have very targeted objectives, mainly two. One, they want to grow a crop successfully, and they want to make profit out of that. And any solution so far we have provided them, it doesn't solve either of those problems. In fact, we introduced more risk in their system without promising any benefit. So we can't really expect farmers to change their practice without offering them any incentive. And of course, there are other when we talk about new technologies, there are other challenges. For example, not all practices integrate into farmers' existing practice. Sometimes the irrigation systems are not designed the way they are supposed to be or the way they are needed. And of course, the lack of awareness in the broader community. But I think, in addition, so we need to look for incentives and be creative about it. So I think there's been some good discussions, and Punjab government is in the process of changing their water pricing to create incentives for farmers to use more sustainable practices. For example, changing the Aviana price. So one of those initiatives is switching from charging water charges based on per unit area to the crop type. Of course, for rice, it doesn't solve the problem because it will just encourage farmers to not grow rice. So, but then there is also the proposal of charging groundwater. That is definitely creating an incentive for farmers, because when they use groundwater, if they are paying price for it, they will want to use less of it, so that creates an incentive. And of course, there are other technologies, for example, alternate wetting and drying, or DSR, or any other technologies. If there is an incentive for farmers within that water pricing mechanism, that can, of course, play a role as well. So greenhouse gas emissions is an important part of this conversation. So Pakistan is only responsible for less than 1% of the global greenhouse gas budget. But we are one of the most impacted countries because of climate change. That doesn't mean that we should not worry about reducing our emissions. We are part of the global community, and we need to play a role in reducing our emissions. And I think when we talk about emissions, so what this graph is showing, this is showing the greenhouse gas emissions from agriculture sector in different countries in Asia. And the blue bars are showing the total emissions in million tons from agriculture sector, and the orange bars are showing the percentage of those emissions in the national inventory of those countries. And you can see, for example, India and China has much higher carbon footprint than us. But when you look at those orange, the percentage of agriculture in that is much lower. That is because they are more industrialized than us. So coming back to why agriculture is important in the greenhouse gas debate, nearly 45% of our emissions are from agriculture. And we have committed under the Paris Agreement that we will reduce 50% of our emissions um, by 2050. So without addressing the emissions from agriculture, we cannot achieve that. So that is one important reason that we need to reduce our emissions. And second, we talked about the incentive. So when we talk about adopting water-saving techniques or water-efficient technologies, the incentive is that we can monetize them by developing carbon projects and exploring carbon markets, particularly volunteer carbon markets, and we can monetize those, creating an incentive. Without that incentive, it's unrealistic to expect any change from the farmers at the farmer's end. Second, we are a major exporter of rice. There is an increasing demand for low carbon rice. You can see that label in the green. There is an increasing number of products that have that label now, and consumers are more and more aware, and they look at that thing and they select the product that has the lower carbon footprint, being a responsible citizen. Second, and the last point on this, different countries are imposing carbon taxes on their industries. For example, European Union's carbon border adjustment mechanism. The way these taxes work, and in many places these are called ETS, emissions trading schemes. The way they work is the government has decided rates on the emissions per ton of emission. So the industries or companies, they need to pay a tax based on their emissions. Now, some of those companies also import products from overseas. For example, EU imports rice from us. So in future, if those taxes are imposed, they will look at they will compare basically, say, the rice that is being imported from Pakistan, India, Bangladesh, they will look at which one has the lowest carbon footprint and they will buy that, not because of environmental reason, purely because of the business reason. So we have more than one reason to consider transitioning towards low carbon technologies. So now I'll request Dr. Ishfaq to present the next few slides.
Okay, so thank you very much, Dr. Hicks, for highlighting the issues related to climate change and its impacts on water resources, as well as few issues related to on-farm water management. So based on this rationale, so we are going to adopt an alternate wetting and drawing approach, which is the innovative technology in order to earn the carbon credits in agriculture sector. So it is not only the climate smart practices, but it also a nature-based solution because it not also enhance the yield, but it also support in climate change adaptation because it save the water, and then also it also support in climate change mitigations because it also reduce the GHGs emission from the agriculture sector. So we are going to adopt a IPCC approved methodology for GHGs emission in alternate wetting and drying approach to earn carbon credits in agriculture sector. So according to the International Rice Research Institute, they have conducted series of experiment and they found that by using this technology, we can save 30% of water as compared to conventional one. And then we can also save on an average 48% reduction of GHGs emission as compared to our conventional methods of rice cultivation. So based on these approaches, we have an opportunity to save irrigation water as well as to earn carbon credits in agriculture sector. So how AWD actually works? So before that, I want to highlight that AWD can be adopted in wet seeding rice. It can be adopted in raised bed sowing, but here we are going to adopt in transplanting rice because it is an approved methodology by the IPCC. So in this approach, basically we measure the overall deficit water using the conventional tube as well as the sensor tube. So in this method, basically we apply the irrigation water and also keep the irrigation water 2 to 3 weeks after transplanting, and then we allow a deficit of 15 centimeter below the soil surface, and then we re-irrigate up to 5 centimeter above the soil surface up to a flowering stage. So when crop reach up to a flowering stage, so 1 week before flowering and then 1 week after flowering, so again we will continue a conventional flooding, which is in the application of water 5 centimeter above the soil surface, and then we again start the AWD approach till 15 or 20 days before harvesting. So this is the basically approved methodology by ERI as well as by the IPCC. So keeping in view this water saving, so we need to highlight the issues of, and also we need to keep in mind the application of fertilizer method because the nitrous oxide emission is also one of the important challenges in alternate wetting and drying because when soil transfer from anaerobic to aerobic conditions and there are some nitrous oxide emission issues in AWD approach. So that's why co-management of water as well as the fertilizer is very important when we conduct this type of experiment on AWD approach. So based on this, we are going to plan a series of experiment in the GHG's emission. So we will measure the nitrous oxide as well as the methane emission and also calculate the overall net balance of these emission in using these experiments. And then our third objective is related to that we are going to develop our own emission factor. So currently, because we are using default emission factor using the tier 1 approach by the IPCC, we are also using our neighboring country, the India emission factor. So that's why there is a dire need to develop our own emission factor in order to earn a carbon credit and using this approach. So that's why we are going to develop our own emission factor. So using these AWD techniques. Our another objective is related to exploring the carbon markets in terms of earning carbon incentive because we will provide some kind of incentive to the farmer if they start adopting this AWD technique. So that's why we are going to explore carbon markets, the voluntary markets to earn carbon credits as an incentive to the farmer who will adopt the AWD techniques. So lastly, we are also going to conduct a series of experiment at a farmer level in which we are going to conduct experiment at almost 160 farmer where we will assess and identify the different barriers related to their social as well as the logistic approaches as well as what kind of the issues and challenges they are facing in adoption of AWD techniques at a farm level. So based on this, we are going to conduct two types of experiment. Our one experiment is basically related to GHG's emissions. So we are going to conduct experiment at Rice Research Institute, Kalashaka, Kushikupura, and another experiment at Okada, which is on the on-farm water management research institute. So there will be basically two treatment. One is the conventional, and other will be the AWD techniques. So why we are conducting this experiment on these two locations because we need bit control environment and also we need some technical labor for that and also we need some laboratory to analysis these GHG's emission and also some plant analysis and then there are some security issues. So that's why we prefer to conduct this first experiment at these two locations. So in this we are going to conduct a randomized block design for this approach because we have two sets of treatment in each block. So there will be total 5 blocks under this experiment and we will place one manual chamber in each block. So there will be overall 10 chamber at each location. So, and total will be the almost 20 chamber for both locations to measure the GHG's emission under this experiment. And our second experiment is related to the adoption of AWD techniques at a farm level. So under this approach, we are going to conduct different sets of treatment. One is the conventional flooding, which is normal practice by the farmer, and then we are going to place some other treatment, which is the AWD with simple tube, manual tube, will be used, and then we will place another treatment, which is the AWD techniques with sensor tube, which automatically detect the soil moisture deficit level, and also it beeps or send a message to the farmer that this level has been achieved. So then we need to irrigate the water. And again, we will adopt another treatment. We will provide advisory to the farmer. So in this advisories, we will provide them how to measure the water, how to apply the water, and then how to take the deficit level in manual as well in the sensor tube. So this treatment we will also consider at a farm level. So overall, we are going to conduct this experiment, and overall 160 farmer. So we will provide advisory to the 80 farmer, and we will not provide the advisory to another 80 farmer. So in this way, we will address the issues, and we will also identify different their problems as well as related to logistic as well as social, and what kind of other challenge they are facing in adoption of climate change. So again, I will request Dr. Riz for the submission.
Thank you, Lisa. So we're talking about emissions, and we thought it would be good to just to touch base on the science of how these happen. When before all agricultural land have been natural systems before they were converted. So when we look at and often these when we talk about methane or nitrous oxide for that matter, when those emissions are more a function of the soil system rather than the crop type. So when we talk about a forest system or a natural system, often the soils are very healthy, and there is a big usually a population of methanotropes, or you can say methane-eating bacteria that live there, and the conditions are relatively drier. So when you put a chamber there and measure, it will be a net methane sink, because basically the methane, that soil is absorbing methane and oxidizing it. So that is good for the environment. Then if you convert that system into, let's say, a crop, which is not a rice crop, which means the conditions are relatively drier, there is very little methane action happens there, because the soils are not very healthy. When the soil is dry, it can be a very weak methane sink, and when we irrigate it, it can be a very weak methane source, and they cancel each other. So often in those, for example, wheat systems, methane is not a very not a greenhouse gas of concern. And then if we convert those fields into rice, we create low oxygen environment, and that's ideal for methane producing bacteria or methanogenic bacteria. So, and then they start producing methane. So basically, it's the soil conditions that determine how the biogeochemistry functions in the soil. And so just a bit more about the first trial, which is about the measuring greenhouse gas emissions. There are many techniques, established techniques that can be used, and some of them, each one of them have some strengths and weaknesses, and we thought we'd just quickly discuss what those are. So one of the common ones is using eddy covariance towers. The strength is that it usually works at 20 hertz, which means you get 20 data points in 1 second, and that's a lot of data, and that's I think the highest and the best biggest strength of the system. And then it also has because it's an open system, you can see it's just detecting from the air, so that it's not an enclosed system, which means it covers a large area. So you can put it in the middle of a field, and the footprint it generates, it covers almost a half a kilometer square, depending, of course, on the height of the tower. And these are commercially available. For example, Lightcore is the main company. They are just available off the shelf. We can buy them. And I think the weakness is, particularly from our point of view, we can't use them for flood trials. For example, our interest is to compare AWD with conventional flooding. So we can't do that because it's not an enclosed system. Its footprint is really big. And also, this system is particularly more suitable for carbon dioxide measurements. And all these numbers you see in literature, for example, the Amazon forest in Brazil, that the forest is sequestering this many million tons of carbon, or absorbing this many million tons of carbon. Those numbers come from these air equivalence towers. They basically put these towers on top of the canopy, and it looks at the exchange, how much CO2 is going out of the system and how much is coming in. So, but I think in last 10, 15 years, they also developed some methane and nitrous oxide sensors for these. But the sensitivity, there are large uncertainties, and the sensitivity is not that good. So they are still not the preferred uh, technique for methane and nitrous oxide. So another one, these are the enclosed chamber systems. So this can be automated or manual. So this what you are seeing there is an automated chamber. In fact, this is a picture from my postdoc 10 years ago in Australia. So this the strength of this system is that um, they open and close automatically themselves in that white box that you can see there in the picture in the left bottom. There is a gas chromatogram sitting there. It just chamber closes. It's there's a pump that sucks the gas sample, it feeds it into that GC in that box, and you get the data instantly. So you get a data point every 3 hours, which is ideal. But the problem with this one is that these are just connected with the system, so you can't move them around. If you want to move to a different location or you want to cover, for example, we are planning 2 locations. We can't do that with this. With this, all of these chambers have to be in one location. And there are just so many things that can go wrong. For example, in the right bottom, you can see that chamber, the number of cables and tubes. You can see, even in the developed countries, the downtime for the system is very high. And it happened to me one day. I used to visit this system every day, but in the afternoon, so there is a risk of downtime. But also the GC system in that box, it has a radioactive source in this. So the sensor that measures nitrous oxide, called ECD, it has a, I think, nickel radioactive source in that. So of course that is a high risk. I don't think anyone will allow us, the particularly Atomic Commission, to put this thing in the wild. So, so the system we are going for, considering all these reasons, is the manual chamber system. This is a very simple system. So basically, it's just a chamber. It can be made from different materials because we are enclosing plants in it and they need light. So we will make them from acrylic. It's transparent. So that gentleman in that picture, basically you close that chamber, put it on a small area, and then you take the sample with a syringe like that gentleman in the picture is doing. And then you convert that, you transfer that gas sample into a glass vial in the middle bottom picture shown. And those samples are then sent for analysis using a GC on the right bottom side. So we, of course, has the strength of this system is, you can put these chambers anywhere. So we can create 5 sites and we can just keep transporting these chambers because there is no wires attached to this. There's a low maintenance. Of course, this is a labor-intensive exercise. We need to send the gas samples somewhere for analysis. Often it's hard to get a functional GC in Pakistan, so we are planning to send them overseas. And also, we need to ensure the quality of how these samples are collected, how these are stored, how these are transported. We need to ensure those are done in the right way. And the lag, of course, between when you collect them and you send them overseas is usually half the season is gone by the time you get those results back. And if something is wrong, you can't undo that because it's gone. So, but I think we can. These are the challenges we can control in many ways, and we will. So we are potentially considering a significant collaboration with our national as well as international institutes, and you can see their names on the screen. Punjab on from water management, we will be using their research station in Ukara. University of Agriculture, Faisalabad, particularly we are looking for expertise in soil science and greenhouse gas measurements. We also had a very good meeting with Rice Research Institute yesterday. And we will be using one of their sites for one of the trials for greenhouse gas emissions. We have a collaborator from University of Philippines who is ex-IRI, and he's one of the scientists who was originally responsible for developing this AWD technique. And then, of course, the Queensland University of Technology in Australia and KIT in Garmisch in Germany. They are the two institutes that they are world leading in research on greenhouse gas emissions. So we are exploring collaboration with them. So these are not set in stone yet, but we are talking to them continuously, and hopefully we will finalize these collaborations in the coming days. So just wrapping it up, the impact and outcomes for this work we think is this will be the first ever study on greenhouse gas emissions in rice systems, both for continuous flooding and for alternate wetting and drying. So the data that we'll generate, the emission factors that we will generate out of this, we can use them to improve our national greenhouse gas inventory. So as per, we are a signatory of Paris Agreement, which is a legally binding agreement. And we need to report our greenhouse gas emissions from each sector regularly. And right now, we don't know what the emissions are. We are using those emission factors that come from other countries, basically. So there is a large uncertainty. This will develop more confidence in the quality and accuracy of that data. Carbon markets, again, this is very important. I think if we really want to improve, we need adopt if we want the small farmers to adopt techniques like AWD, we need to generate an evidence. We need to offer them something. Without that, I don't think it will cut it. So, as I mentioned before, there is also a demand for low carbon and rice, as well as low water footprint rice. And with this, we can demonstrate in very clear terms, with solid evidence, what our carbon footprint is. Right now, we can't even talk about our product carbon footprint is high or low because we just don't know. So this will be the first time we will develop the carbon footprint of our rice. And if it is high, then at least we have a baseline. Then we will work on reducing that footprint. Of course, we are talking about without government's interventions, without those pricing mechanisms, it is hard to adopt those technologies. And for any policymakers at the government level, those policies need to be based on solid data and evidence. And we will generate that through these trials the best we can. And of course, it's not easy. But changing farmer practice is not easy. And AWD is no different. There are challenges. It has been trying, I think this AWD has been in market for like more than 2 decades, but adoption is low. And we want to understand that more. We have some idea, but we want to understand it more. And more importantly, try to address those adoption barriers. Thank you.
Now for the question answer. Anyone has a question, please raise your hand so that the mic